So now we are going to look at some other enhancements for heat transfer. So what can we do to the fin for two purposes? So one purpose is to improve the heat transfer coefficient on the air side, and another is durability. If any of you have friends who stayed closer to a drain, then many times air conditioner coils, condenser coils will just crumple, and after 2-year period people have reported losing the condenser totally. So that is a symptom of corrosion. Some gases containing hydrogen sulfide tend to react with aluminium and cause it to corrode faster than, or people staying near the sea many times have reported some particular condensers wear off. So one way to offset that is to provide a coating, and this is a newer problem. Earlier, say air conditioners manufactured 15 years back, 20 years back, the fin thickness was in the region of 0.2 millimeters. There was enough thickness on the fin, so one would not notice. It would easily last for the 12 years or 10 years life of the air conditioner. Now with competitive costs, fin thicknesses have gone to as low as 0.11 millimeters, and with that low thickness, if there is any corrosion that begins, it is very easily evident, and to offset it, we provide a 1 to 5 micron thickness on the fin, and that takes care of corrosion. So that is one purpose of coating a coil. When we are talking about enhanced fin surfaces and edges, so how do we enhance a fin? If you have a plain fin, there is a straight flow path, the pressure drop is the least of all configurations, and we would have a certain part of the air pass through, like bypassed, because it would not come in contact with the fin. So to enhance it, we could look at, first step is corrugating the fin. So instead of having a plain fin, so the first one that we see on top is a corrugated fin, and then you could have variations in the edge of the fin. So you could have a straight fin, or you could have a ripple edge, and all these are means of improving turbulence, increasing the turbulence and getting a better heat transfer. And finally, we cut the fin. So before it is assembled, make louvers in it, so that there is further turbulence generated in the path of air. And all of these types can be used in evaporators as well as condensers. If you look at characteristics of flat fins, they are the ones which will reduce ice accumulation. So if you are looking at a frost-free refrigerator, then we normally see plain fins being used. They have the lowest air resistance, as we mentioned, and then applications are deep freezers, cooling and freezing systems, and then passive airflow systems. Corrugated fins improve the heat transfer, but it is less than a louvered fin, and they have a lower resistance to airflow in comparison to a louvered fin. Wherever there is dust, so typically condensers will make use of a louvered fin, or if we are looking at off-road vehicles, then there again louvered fin is a good choice. There have been two fin forms that have been in the market for reasons of some patents. So someone filed a patent for a particular shape of this fin, and that was a sine wave fin with and without lancing, and for that reason it was protected, and therefore people tried to beat that by making a louvered fin. So there have been two fins that have been in use, louvered and sine wave, pretty close to each other, but the sine wave has a better heat transfer than the louvered fin. The corrugated fin, not the louvered, the corrugated fin. And then the sine wave is again a general all-purpose selection. When you are bothered about clogging, it is less prone to clogging than a louvered fin, and it is a default fin shape also. If we are not specifying anything, then this could be the default fin shape that we use. The louvered, we have talked, is the highest turbulent generating fin, and it is also offering the highest rate of heat transfer on the air side, and it comes with a penalty, which is higher pressure drop. But they have been used so much that the trade-off has been accepted. So when you go to a fin density as high as 18 fins per inch and a louvered fin for evaporators, they have been helping manufacturers build compact indoor units that have been also acceptable to the market in terms of cost and performance. So if you look at the summary, we have the basic plane fin, and then we have the corrugated fin, the sine wave fin, and on top for performance is the louvered fin. Just like we can enhance the fin surface, we can also enhance the tube internal surface. So reference is plane fin, and then what we have is a rifled inside. So we have grooves, and these grooves again generate turbulence and improve the inside heat transfer coefficient. So refrigerant side heat transfer coefficient inside the copper tube goes up. Now I have shown a visual, and I do not think this is clear enough, or is it? I think it is clear on for your screen. I think it is pretty good. So let me just see. If you look at this surface, it is a different internal surface. The type of channels, it is a crisscross pattern, and there are manufacturers who have protected their patterns and got some mileage out of it, getting a premium. And then this is having two spiral grooves, so it is like double rifled, you could use that word, and this is a simple spiral groove inside the tube. So as manufacturing processes for drawing copper tube have evolved, it has been possible to make some more complex shapes inside the copper tube and get higher refrigerant heat transfer coefficients. The key thing that we must remember is that this becomes necessary only after you have taken the air side coefficient substantially high, because otherwise the air side heat transfer coefficient is what is the constraint in the amount of heat that we will transfer. And then there could be further turbulence generated by inserting something like a spiral wire inside the tube. So this spring kind of arrangement further enhances the thing, and it is used in different designs differently, because if your intention is to enhance the heat transfer coefficient in a certain area of the tube only, then because there is a cost and complexity associated with implementing such a enhancement, you would do it specifically for those tubes where you want to benefit from this. Now why I am bringing this alive is that there is a region in the evaporator where there is superheat happening, and when the superheat is happening, there is really no major benefit of putting in an enhancement device there, because it is all vapor. So suddenly, from a mixture of liquid and vapor having fantastic heat transfer, it goes up to its maximum just before it reaches superheat. So we need to be careful on what part of the circuit we are adding the enhanced surface in. So now if we look at everything that we have discussed about fin on tube design heat exchangers, then whether it is an evaporator or a condenser, we would need to define all of these. So we need to define the material, we need to define the fin thickness, we need to define spacing, and in a little while I will also take you through the coating part. So these are the parameters that are expected from an engineer when he is designing the evaporator or condenser. And then similarly on the tube side, what is the material of the tube, outer diameter, tube thickness, tube spacing, and when we say tube spacing, it is the vertical pitch as well as the transverse pitch, and the internal surface type. The governing equation is, the overall governing equation is overall heat transfer coefficient area into log mean of the temperature difference at inlet and outlet. There is something more complex than this, because the evaporator does not have a constant temperature profile. Let us say comfort application, return air entering at 27 degrees centigrade, dry bulb, 19 degrees wet bulb. When it first comes in contact with refrigerant, the bank of tubes which are the first contact point, we will have only sensible heat transfer. There is no mass transfer happening till that air reaches the dew point. Then within that section there could be a certain part which is in the superheat zone, So, the inside heat transfer coefficient is not the same. So, if we want to do a thorough analysis, then a simplistic calculation will not give us an accurate result. So, we would need to look at a software solution where we define small elements of the heat exchanger and do the mass transfer and heat transfer balance equations for each of them using all the knowledge that we have, all the theoretical knowledge we have. And then we would also look at validating some of them by doing some experiments, because all our assumptions will need to be validated, and then that software becomes useful for simulation, for predicting designs and all that. Now, fortunately, in air conditioning there have been so many products developed that there is a set of values that are very handy. So, you could today look for the heat transfer coefficient inside a tube for R410A, R22, R134A, and use that as a starting point for your design calculations. Similarly, the air side heat transfer coefficient for certain velocities are available in literature. So, that allows us a good stepping stone to the first design. But today in the competitive world, if we are going after optimization and the best performance or the best cost, then we need to have a means of iteration. Iterating number of circuits, iterating the face area, iterating the hairpin length and all that, and for that we will need to get into more detail about doing some calculations. And now the main difference when designing an evaporator and a condenser is that in the condenser we are increasing the temperature and there is no mass transfer involved. So, if we have done an evaporator design, then designing the condenser is simple. It's just that we are rejecting heat instead of taking in heat to the refrigerant. Now, I will go into a little bit about the coating, which is different for condensers and evaporators. So to differentiate the kind of coating that we use, the one purpose of coating is to enhance the life, which means fins don't crumble when they are in corrosive environments. And we could do that by using stainless steel or copper with tin coating, or we could use aluminum with some special coatings. So, one such coating which is used on evaporator coils, which does a combination of things. One is to enhance the life, which it could withstand a salt spray test of say 500 hours, and it also changes the characteristics of the surface. So, the wettability of the fin surface changes, and that has two benefits. One is the condensate drains faster, the film thickness, the vapor film thickness on the film is reduced, and carryover of droplets into the supply air is reduced. So, these are the benefits. So, you can see in the two figures when we use the enhanced sorry, say again.
You mentioned that salt is
there is a salt spray. So, let us say we go for a coating to enhance the life of a fin, right. How do we measure? So, a supplier may make a claim, but as a manufacturer manufacturing the appliance, you want to test it out. So, you look for a parameter. So, there is a salt spray test. So, in a humid environment where there is so you use a spray which consists of salty water and you subject that part to 500 hours. So, if it withstands 500 hours, it is considered adequate for the life of the air conditioner. So it is a robustness test, and we will look at robustness tests also in subsequent lectures when we are trying to look at how to make a product robust in field. So, different unexpected scenarios in which the appliance needs to work, have we done anything to prove it in the lab at the prototyping stage. So here is the angle of contact. Because the surface tension changes, so the angle of contact changes from 75 degrees to 10 degrees, and this leads to better flow of condensate into the drain pan. This becomes handy when there is a lot of high air velocity in certain parts of the evaporator. The droplets being thrown in a tangential blower because of the velocity being high in certain part of the coil, it addresses very well. So, split systems you will normally see split systems have a blue coil, and that is an indication that a hydrophilic coil has been used there. And a split system has a tangential blower, So, it would have a tendency to pick up droplets more than a window air conditioner or a ducted air conditioner chiller. So, then an exact opposite of hydrophilic is hydrophobic. So, here we want to repel water from the fin, so that it is easily dispersed into the environment, evaporated, and does not create clogging kind of characteristics, and this is useful in condensers. Here the salt spray test demands are also much higher. So, if we were to test a coating, then we would anticipate it being good for more than 1000 hours of salt spray test, and that is because outside air is not so controlled. There is likely to be more corrosive gases. It is subjected to storms, dust, and all that. So, another claimed benefit of the coating is that the surface remains free of dust. So, the chemical that is being used for coating it is being developed in a way that it does not allow dust to stay stuck on it, and the material is an epoxy material. Then this is a residential duct free split air conditioner coil, and here are some openings which would include passage of refrigerant into the coil and out of it, and the complexity in circuiting can be seen from a tripod here. So, this is actually the refrigerant bifurcated into two paths after one pass through the heat exchanger. We would do that again to optimize the heat transfer, and most of the literature today has been simplistic in how to predict heat transfer in coils by not accommodating such things which are already in use, which is splitting the refrigerant path midway, unequal circuiting, and all that. So, with whatever I was trying to even in preparation for this class today, whatever I saw, there isn't enough to predict this kind of behavior. So, one thing I have taken on is to see what is the closest we can get to. Like if we can get to single equal circuit, then we would work with that and provide you that information as a means to do the design. But as engineers, we have to do a design, right? So, if formulations are not available, if we don't get the exact equations, we still will need to do a design. So, another approach is to look for known systems with a known performance, and then we can look at scaling them. So, if we have a unit which performs well at 5 kilowatts, we want to scale it up or down. One of the simplest things to do is to use a correlation, and while that looks simplistic, in actual design, benchmarking is a standard procedure. So, let us say if today I was working in any of my earlier companies, before investing on a new design, I would invest on benchmarking. I would buy competition units, compare with the best in class that would be there in the company I work for, and see for myself what cost and performance is already available and what is it that I can target using that knowledge. It also becomes a good place to test all the known correlations, software algorithms, and tools that are available to an engineer. Then if there is a constraint of time and you cannot have the most accurate correlation, then you would go with using that information and predicting the first performance of the coil. So, you could for example make a choice here. If we took a coil like this, put it through a test in an actual system, we could see circuit by circuit superheat. Now, circuit by circuit superheat will tell us how evenly the coil is designed, and one easy balance point would be to add a hairpin to the circuit which has the least superheat or no superheat, and remove the hairpin from a circuit which has a very high superheat. So, we would have reduced heat transfer in one circuit and added heat transfer in another circuit, and the attempt would be to balance it out. So, that then takes us to the domain of prototype testing and benchmarking and comparing circuits. And when I started working initially, and this is 1993 onwards, I did not have very sophisticated design tools available, but I had test facilities and an opportunity to rig up sensors, sight glasses, a liquid indicator basically, and check out what's happening inside. So, and then we ran a project of course with IIT Delhi, and that was to develop some software to predict performance of evaporators and condensers. I think I mentioned once earlier in my class that when the founder of air conditioner started designing coils, he did not have access to any known literature or correlations as to how he could predict performance. So he went by the first principle: test, develop correlations, and then use them to design systems. Now, if we look at this coil, this will typically go into a residential duct-free split of this nature, and you can see the complexity. From evaporator design, we would also need to look at several other components, and the key component there would be the supply air fan. So that is a tangential blower which consumes in the region of 20 watts of power. The key concerns there are totally different from heat transfer. So you want low noise, you want ability to adjust speeds, and a certain resistance to carryover of refrigerant droplets. Then in addition to that, there would be factors related to aesthetics. The coil, bare coil by itself would not look very elegant, so we need to cover it up, and you need to have some means of having access to the filter, because that would need more frequent cleaning. So from design and selection of an evaporator coil, we would end up looking at the full gamut of components which would be needed. So we have looked at capillary before, and then there would be a filter dryer to ensure that the capillary does not get choked, and compressor selection we have handled before. Then when looking at compact heat exchangers, for condensers typically it is common to use circular designs like this, or U-shaped designs. And then this gets into a condensing unit. So from a condenser we migrate to looking at a full condensing unit, where we have the compressor that we earlier looked at, how we selected it based on the ambient and the evaporating temperatures, and then we want to look at the control components that we need to integrate with that. So in a condensing unit, other than the coil, we will need some means of mitigating any additional noise, and then some pressure switches if it is a large condenser, to protect the compressor from operating outside its design limits. We would put in sensors that would signal the controller to switch it off if there was any untoward thing. And things that we need to be aware of is again clogged coils, refrigerant leak, high discharge gas temperatures, and all that. In terms of choosing materials for making a condensing unit, we would look at corrosion resistant steel. So galvanized steel would be a common choice, and then we would look at powder coating it. We would look at shape so that there is a certain quality of manufacturing that is possible. There is a certain repeat in component to component, and you can see the condenser coil circuiting on this side. So one end of the coil would have headers, finally connecting it to a discharge tube, and the other end would be the liquid line which would go to the split system, other end of the split system. This is the hairpin side of the bent condenser. Now if you look at systems in residential air conditioning systems, other than window and split, there could also be variable refrigerant volume systems, where multiple indoors can be connected to a single outdoor, and there could also be hydronic systems where we use water as the heat transfer medium to look at multiple indoor units. And then there are also options like geothermal air conditioners and heat pumps, where we are either rejecting heat into the groundwater, or we are taking heat from the groundwater if it is a heat pump application. Today residential systems have become so popular that this picture says it all. Each apartment is having several of these units, right? It's more like an exhibition, right? And this is growing. So in India, the penetration of air conditioners is still to reach the levels that we see in China and other developed countries. So we are lagging by about 10 years. So right now there's going to be tremendous opportunity for air conditioners to grow in India. We're just about at a stage where people are beginning to add from one to going to more units in the same household. Then we've looked at different coils before already. The one unique thing here is a coated condenser coil here, and then a bare set of tube banks. So where there is no major enhancement required on the outside, then something like this can also be used. This and this would typically be parts of a window air conditioner, which is again a residential air conditioner, like this. And here you have the expansion device would be a capillary tube. Because of cost, it will be a low cost device. Here is the user interface. So we talked a little about how to change the temperature, select on off controls, and some display. So we would have a display here, some means of removing the filter, and the components inside I'm sure by now you're all familiar with. So we have the evaporator on this side, the condenser on this side, and then here's the evaporator, and this is the supply air region. There's another view. Now when we are looking at ductless split units, we could look at conventional systems which are fixed speed systems also connected to multiple indoors, and this is one example of that. Now inside this unit there could be a compressor which is either modulated digitally, which means the compressor continues to rotate but the compression is switched on and off. When we looked at compressors, we looked at two different ways of variable speed. One was true variable speed where the compressor motor changes speed, another was we modulate the duration for which the compressor is in compression and then it is offloaded, so it's unloaded and the scrolls just continue to rotate without doing any compression. The key feature of ductless split units is the very name. You don't need a duct to spread air in the conditioned space, and for that reason they are simpler to install, maintain, and service. Then these are some other types of units into which we will end up having evaporators designed for. These are becoming less and less popular, but if it is a large room you could consider unit of this nature. Then we have in ceiling cassette units, and these are the ones where I was mentioning the need for a condensate pump. If you need to have it in the ceiling, the design is such that you need a pump to ensure condensate is thrown out. Wall mount, I'm sure all of us have seen and are familiar with. Then I have another picture on the condensing unit where we can see it from another side, and here we can look at the fan, and the condenser fan is normally a propeller fan. So we would look for a fan which is different from what is used in the evaporator side. In the evaporator side we are addressing a heat exchanger which has both simultaneous heat and mass transfer. So there is high resistance there. Then there is an air filter, we need to compensate for that. So we end up using a forward curved blower in most cases, or a tangential blower in duct free splits. In condensers we would use propeller fans when they have generally made of plastic with a motor, and in some of the more advanced designs they would be driven by a DC motor. Again, the ability to modulate the airflow so that we can address varying ambient conditions, outdoor air conditions. These are some means of looking at the interface between the user and the unit. So what is it that we would like to see? When you are using an air conditioner, ideally what is it that you would like to see or control? So very basic, on off everyone wants, ability to adjust temperature everyone wants, but beyond that what else would you want? Yeah, ability to switch it off when after a certain known time, right, or switch it on before you come to the home. Good. If I were to look at my wish list for an air conditioner now is that I should enter a room, I need to do nothing. The room should know that I am there and what is my preferred setting, and everything should be, even before I enter the room, it should be air conditioned. I shouldn't see it, I shouldn't hear it, I should just feel the comfort. And if you look at a lobby, go to a 5-star lobby, you don't hear air conditioning, you don't see it, but you're pretty comfortable because of the size and the way the air is distributed. So ideally, that is what we want, right? We are in the bedroom, air shouldn't be coming onto our face, we shouldn't be struggling with adjusting the louvers. Whereas in the market, a marketing gimmick is to sell adjustable louvers and positions of louvers in a duct-free split, so that you can point the air in a particular direction. If you look at it from a real need perspective, where is the need? I'm standing here, I'm comfortable, I don't need to see the air conditioner or do anything like that. But these are gimmicks, and sometimes useful gimmicks because they differentiate one product from another, and they actually help put some premium on the product. So some of these fancy remotes would mean that the air conditioner would be sold at a higher price also. And I have myself contributed to adding features in some of the companies that I've worked for. We've added features so that we can differentiate, and it's becoming more like if everyone in the market is doing, then you also need to do. But look at it from a need perspective. When you connect with air conditioning, what is it that you need? I agree, there are times when you need to just have humidity lowered, but then it should be known, right? Because human comfort is defined. 25 degrees, if you maintain 50% more or less, some adjustment, fine. User A needs 22, user B needs 26, done it, and then it's over. But then for whatever it is worth, these units will allow for settings that can make the compressor run for dehumidification, and it is typically an algorithm. So instead of honoring the set point, then the compressor is switched on and off in response to a particular cycle. So you want to dehumidify the room without respecting set point, you will probably overcool it, but then you will cause the compressor to continuously run and then stop and then run at the lowest fan speed. So that reduces the sensible heat factor and increases the latent heat factor, and then that would address that. You could also have some things like reminding you that it's time to change the filter. So you get an indication on the unit. Sometimes have multiple units, so you want to define which remote will switch on which unit. So you can again play with that functionality. You could program that, fine, this is the unit which will operate units on the left hand side, this will operate on the left, all these. Then this is an example of a central controller. If you have multiple units at home and you want to control all of them from one place, then this would be wired and it would have some algorithms to communicate with the multiple set of units, which you could assign addressing systems and all that. This is an example of selling a feature again. Some time back it used to be I feel comfortable, or I feel warm, or I feel cold. So you just give that as a signal to the unit, and then the set point is altered in response to that. So if I'm standing here and I'm feeling slightly cold, I would press a button and it would alter. So as it wouldn't be, the user is not pushed into determining what temperature he should maintain. He is simply giving a signal on how he's feeling. Yeah, the key thing in the previous slide, sorry about that, was that the temperature sensor which is controlling the compressor on off is located in the return air path, very close to the evaporator coil over here. So when we are altering the set point, we are actually altering the temperature here, and the key difference in this feature is that you are making the air conditioner respond to temperature where you are. Again, that feature is not needed if the entire space is at a uniform temperature. Then we look at multiple VRF systems, and the whole value proposition for a VRF system is the ability to get annual energy savings. So in this figure we can see multiple indoor units. So we have several of these terminal units all connected through a common piping and distribution of refrigerant. in a residence, not all rooms need to be air conditioned all the time. So that is the basic value proposition that gets built in multiple VRF systems. So first is you get to downsize the total required capacity of the air conditioner, and to relate to it, think about your own homes. Do you need to air condition the drawing room and all the bedrooms at the same time? Most likely not, right? But when you have guests, you would want all the bedrooms air conditioned, and when you are having a get together, like an evening get together, the bedrooms don't need so much air conditioning, but the living room has a lot of guests, so you need air conditioning there. So a system like this will allow for the variation, like they would adjust to those needs and the intention is that it should happen at a lower installed cost. But if you look at figures today, we haven't reached that yet. So very simple, when I was buying air conditioners for my home, I was looking at, could I buy a 6-ton unit which would take care of 3 rooms plus the living room, and I found that no, the cost was going almost double or 2.5 times at that time. So it didn't make sense. But if you look at it from a pure engineering point of view, the total installed capacity, there is an opportunity to get it down and also to get benefit of annual energy savings. So when we have a system of 6 tons which is coupled to just 2 indoor units of 1.5 ton, which I would guess would be a normal residential air conditioning need, then the condenser coil is oversized and it can be used to run the compressor at a much lower condensing temperature, allowing for a higher EER, a higher part load EER. So this benefit is only optional and available if we use VRF systems or some system similar to that. If you look at just the systems, then here this is what an outdoor unit would look like, and the outdoor unit then is connected to several indoor units, both through the refrigerant piping and also through the controls. And if you look at the complexity, we need to know what is the cooling demand in each of these indoor units. It needs to be consolidated at one point and then determine what compressor speed should be operated to address that cooling demand. And then the compressor speed variation or the refrigerant flow variation can be done in 2 ways. One is using a true variable speed compressor which would offer much higher part load efficiencies, or using something like this which is equivalent to bypassing hot gas. But in effect what we are doing is we are unloading the compressor by moving one of the scrolls up so that there is no compression happening. So the origin of the inverter technology is Japan, and now it is spread across the world, and the prices are coming down because more manufacturers have developed the capability. So particularly after some of the major manufacturers in China have mastered the VRF, that prices have become more reasonable, and it is not so premium now than it was 5 to 6 years back. So the digital scroll technology is from Emerson. So Copeland is a brand of Emerson, and we touched upon how this is unloading. It is found to be effective if the part load does not go below 40% for a substantial period of time, then this seems to be giving some energy savings. But if you really want to go down to 30% of load, then variable speed drive is the right solution. Here you have a DC motor, so the losses at low speeds are minimized. You could have a much higher part load efficiency with a DC motor than you could have with a AC motor. This is an example of a ducted system. So very large air-cooled condensing unit with compressors here, and then it's connected to a cooling coil supply air fan, and then we see the ducts which would be servicing the home. Now here we don't have as much of complexity surrounding distribution of refrigerant to different rooms and indoor units. Is to complete the ducted split, the airflow is something of this nature, and this example actually is more of a US home where in the basement you have the air handling unit, the indoor part of the air handling unit, and then it is directing the duct through different parts. So if you want to look at the components that we discussed, then here is the evaporator, the blower, and if we were to put in a furnace, if there is a heating need, then the furnace part would also be included. Okay, so here closer to what we started with, evaporator designs, including the expansion, the condensate, drain pan, and the inlet outlet connections. So all that is there. So for today we will close here.